In this video, we will determine how much energy your skin will absorb from a UV photon of approximately 125 nanometers. We'll also solve the energy of a mole of these same photons. So in order to solve for this, we're going to use the following equation, which is energy is equal to Planck's constant times the speed of light all over wavelength. Now both Planck's constant and speed of light are two constants that we're going to use. So Planck's constant, which is also h, is equal to 6.626 times 10 to the minus 34 joules times seconds. And our speed of light, which is also c, is going to be used as 3.00 times 10 to the 8 meters per second. Our wavelength is going to be lambda. So now let's plug in the values that we know for this. We do have our wavelength, which is right up here, at 125 nanometers. We won't be able to plug that in directly into our formula, specifically because the speed of light is in meters. We can't take nanometers and meters and put them together in the same formula and expect them to cancel out. So the first thing we need to do is convert that 125 nanometers into meters. The way that we do that is quite simple. We'll use this relationship. Now for every 1 meter, we're going to have 1 times 10 to the 9 nanometers. So as we do that math, that is going to come out to 1.25 times 10 to the minus 7 meters. Now that we're matching with meters with our speed of light, now we can plug this in. So our energy, E, is going to be equal to Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds, times our speed of light, 3.00 times 10 to the 8 times meters per second, all divided by our wavelength, which is 1.25 times 10 to the minus 7 meters. Now looking at our units real quick, we see that we have meters on top and bottom, so those will cancel out. We also have this seconds times per second. Another way to write that per second, if that's a little bit confusing, is per second is the same as saying 1 over seconds. Because of that, we now have our seconds over here to the left. We have our per seconds, or our 1 over seconds there on the right. Those will also cancel each other out, leaving us only with joules, which is exactly what we want because energy is measured in joules. So as we do the algebra, multiply and divide everything out, what we'll end up with is energy is equal to 1.59 times 10 to the minus 18 joules, and that's for per photon. All right, now on to the second part of the question, which is what is the energy of a mole of these photons? In order to do that, we're going to use the following equation. Now our energy, we desire this to be in joules per mole. Right now it's in joules per photon. So in order to get that to where we want it, this is going to be equal to energy of our joules per photon multiplied by Avogadro's number. Which will be in units of moles per photon. Excuse me. It's going to be in photons per mole. And Avogadro's number, if you don't remember, is 6.02 times 10 to the 23. This again will be units of photons per mole. So now let's plug in all the values that we have. So our energy, which is in joules per mole, is going to be equal to our energy of joules of photon, which we have right up here, It's 1.59 times 10 to the minus 18 joules per photon, multiplied by 6.02 times 10 to the 23 photons per mole. Now again, looking at our units, we can see that we have photon here on the bottom of the fraction as well as on the top. So as we multiply these two numbers together, those are going to cancel each other out, leaving us with joules on top and mole on the bottom, which is exactly what we are looking for. So our energy in joules per mole is going to be equal to 9.57 times 10 to the 5 joules per mole.